Okay, now we're going to start chapter 2 in the trigonometry textbook. Chapter 2 is titled Acute Angles and Right Triangles. And so if you remember during chapter 1, I made a separate video that wasn't involved with the textbook, that was just on the definition of trig functions in general. And in that video, I talked about the different perspectives of how you can view the definition of trig functions. So one perspective is mainly focused on in chapter 1, and that's the general definition. With the xy coordinate system, you have any angle that's represented from standard position, and at any angle you can create a right triangle, and then the legs of the right triangle are x and y. They could be negative or positive, and so you define trig functions for any angle. That was one perspective, and again, that's what we focused on in chapter 1. But another perspective that we talked about in that video was you can just strictly think about the trig functions of the angles in a right triangle. So not a right triangle in the sense of we would always draw a right triangle in the general definition. No, like an actual right triangle that you would see somewhere. Like, in other words, a right triangle, in any triangle, the lengths of the legs can't be negative, right? In the general definition, we had legs that could be negative, but that was just for the setup of the general definition. What I'm talking about here is you could just be dealing with just a random right triangle that has angles other than the 90-degree angle of, let's say, beta and alpha. And so you could be looking at any right triangle and you can think about what are the trig function values of either one of these angles. And this is where the SOHCAHTOA mnemonic comes in. SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. That's what you do. You come to the angle you're interested in, and you can get, so sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And you would do the same thing for if you were working with this angle. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Okay, and so that's mainly what we're going to focus on in this chapter. We're going to analyze trig functions of angles within an actual right triangle. And so notice, though, that the other than the 90-degree angle, so the two angles outside of the 90-degree angle in a right triangle have to be acute angles. Because if, let's say they were 90 or above, let's say that this one was 90, well, then 90 plus 90 is 180. The other angle has to be 0. It's not a triangle, right? And so that's what the title is talking about, acute angles in right triangles. So with right triangles, we're always finding the trig functions of acute angles. Now, I do want to make it clear that it's not like we're going to get some different trig function definitions. This is just a different perspective of looking at trig functions. At the end of the day, you could take any angle within a right triangle, it's going to be an acute angle, and just go apply that to the general definition as an acute angle to get the trig function values of that angle. That's fine. That general definition is universal. It's just a different perspective when you look at it strictly from like an actual right triangle, where like you could have like angles upside down like this. You know, we didn't really do an angle like this with the general definition. Or this angle we did, but not beta, right? You can't kind of put this triangle onto the general definition graph and create beta. I guess you have to flip it. You have to flip it around into the page, and then you could do that. Okay. Now we are going to, in section 2, we are going to deviate from right triangles a little bit. We're going to talk about trig functions of non-acute angles, and the textbook is just going to give their own analysis on how you can approach analyzing non-acute angles with the general definition. But in general, this chapter is about acute angles and right triangles with trig functions. Now, before we get into this, note that, so we're, in this course, we're in a plane, right? We're always in a plane, the plane of your computer screen. But you can think about how you could be looking at a right triangle in any orientation in all of 3D space. And then you can think about, okay, what are the trig functions of the acute angles of the right triangle? In fact, no matter what the orientation, you could always do the SOHCAHTOA, opposite of hypotenuse, no matter what the orientation is, right? You could always identify the hypotenuse of a right triangle easily because it's across from the right angle. But then no matter what the orientation, you just do the SOHCAHTOA. But again, though, let's say that the computer screen is in this. This is like the, I guess, okay, so this is X, Y, Z. This is the YZ plane. But, you could think about a right triangle in any orientation. I could take this right triangle here, and we could bring it into this plane and turn it upside down. Right? And it doesn't change anything. You just imagine that you're looking, you're looking down at it or whatever, or looking up at it, and then okay, so what would it be? I guess this is alpha, this is beta, and it's the same idea. Okay, so here's the opening image to this chapter, and it just says that trigonometry is used in safe roadway design to provide sufficient visibility around curves as well as a smooth flowing, comfortable ride. And I'm not sure what they're talking about there. But yes, trigonometry is very powerful. I think it's these examples like this when I was in school I found kind of annoying because it seemed to really oversimplify applications. Like, well, I could take this trigonometry course and now I'm ready to go design roadways. But yeah, you are going to apply trigonometry a lot more than you realize to solve problems, as an engineer, for example. Okay, and just to clarify a little bit more, I don't think chapter 2 or like even this section is all about trig functions with right triangles. I think what they're doing is, so at the end of the previous chapter, we were introduced to the general definition of trig functions, and now here we're going to focus on acute angles and look into trig functions of acute angles in detail, which inherently involve actual right triangles with real, non-negative side lengths. And in the next section, we're going to focus more deeply on obtuse angles, or not just obtuse, but angles that are non-acute. And then we're going to actually look at, in the section after that, we're going to look at applications with right triangles. So you can see here, we're still going to be talking about the general definition, but in this section we're taking a much more detailed look at acute angles, trig functions of acute angles. Okay, so right triangle based definitions of trigonometric functions. Angles in standard position can be used to define the trigonometric functions. There is also another way to approach them as ratios of the lengths of the sides of right triangles. Figure 1 shows an acute angle A in standard position. The definitions of the trigonometric function values of angle A require x, y, and r. As drawn in figure 1, x and y are the lengths of the two legs of the right triangle, A, B, and C, and r is the length of the hypotenuse. So yeah, from the perspective of the general definition, an acute angle, you're in the first quadrant, so the legs are always positive, and then the hypotenuse is always positive. So you have like an actual right triangle. But however, this right triangle-based definition of trig functions, it goes a little further than the general definition, because with the general definition, we never think about trig functions of this angle over here, of the right triangle, right? It's always, we're focusing on this angle that has vertex at the origin. Okay, and so here I don't think they say SOHCAHTOA, but they're referring to the right triangle-based definitions of trig functions. They're referring to SOHCAHTOA. And you can apply it, here's the general definition, but you can apply it with any angle of a right triangle. So if this is alpha, any of the acute angles. So you identify the hypotenuse. I'm drawing it in a crazy orientation because the orientation doesn't matter. You identify the hypotenuse that's across from the right angle. There's the hypotenuse. And so you can choose any one of the angles. And you say, so sine of beta is opposite over hypotenuse. Cosine of beta is adjacent over hypotenuse. Sine of alpha is opposite over hypotenuse. Cosine of alpha is adjacent over hypotenuse. And same idea. So the tangent of alpha is opposite over adjacent. The tangent of beta is opposite over adjacent. And so that's the idea. They're calling this right triangle-based definitions of trig functions. That's SOHCAHTOA. But still, though, we've talked about, you can still apply the general definition to an acute angle of a right triangle, because why? You could put it at the origin like this, but for this angle, it's hard to see how you could put this in standard position, but you'd have to flip the right triangle into think about flipping it to where this edge comes out of the page towards us, towards the viewer, and then flips to this side, and then you could put it in standard position. So you could think about putting either of the acute angles of a right triangle into standard position and then doing SOHCAHTOA on the vertex angle. We did use SOHCAHTOA for right triangles in different quadrants, but the difference was that, a lot of times we weren't actually finding trig functions of this vertex angle. And then when we did it, we had negative side lengths a lot of times. With an acute angle in the first quadrant, we're actually, that vertex angle is the angle we're actually considering, and then the side lengths are always positive. But again, you could come to a triangle in any crazy orientation in 3D space, a right triangle, and you could be viewing it upside down, whatever, and you could say, okay, I'm going to find the trig functions of this angle, and it's opposite, adjacent. Hypotenuse is across from the right angle. Right? Doing it this way, you're straying from the general definition, but that's fine. And so that's all this is about. That's SOHCAHTOA, side adjacent to A over hypotenuse, side opposite A over side adjacent to A for tangent. Okay? Find the sine, cosine, and tangent values for angles A and B in the right triangle in figure 2. So for this angle, opposite, hypotenuse, adjacent. For this angle, opposite, hypotenuse, adjacent. And then for secant, cosecant, and cotangent, you could, secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so the secant of this angle would be hypotenuse over adjacent. The secant of this angle would be hypotenuse over adjacent. So we're going to work a bunch of example problems so you can get the hang of this. Okay, cofunctions. Here we're going to develop some more trig identities. So figure 3 shows a right triangle with acute angles A and B and a right angle at C. And once again, I'm going to stress, for all these right triangle scenarios that we look at, you can think about this being oriented in any kind of way in 3D space. That's the power of thinking about adjacent over hypotenuse, opposite over adjacent, etc. There's no standard position we have to think about when it comes to these right triangle definitions of trig functions. Okay, the length of the side opposite angle A is lowercase a, and the length of the side opposite angle B is lowercase b. The length of the hypotenuse is C. By the preceding definitions, sine of angle A is A over C, sine of angle B is lowercase b over C. Thus, we have the following. Sine of A is A over C, right? But what is cosine of B? Not sine of B, what is cosine of B? Well, that's A over C, so those are equal. Sine of A is equal to cosine of B for the case of a right triangle. For the case of the acute angles of a right triangle, they're going to be related in this way. The sine of one of the angles is going to be the cosine of the other angle, and vice versa, right? So you could say sine of B is equal to cosine of A, right? What is sine of B? Sine of B is opposite over hypotenuse, B over C. Well, what is cosine of A? Adjacent over hypotenuse, B over C. Okay, similarly, tangent of A is opposite over adjacent, so that's A over B, but that's cotangent of B, right? Opposite over adjacent. And then a similar idea is with the secant. Secant of A is cosecant of B. So in any right triangle, the sum of the two acute angles is 90, so they are complementary. Well, okay, but I'm saying these cofunction identities we're about to talk about are, all of this applies for any right triangle. Everything that we've just talked about here applies for any right triangle. Okay, but the sum of the two angles the acute angles is 90 degrees, so they are complementary, and that makes sense, right? Because this is 90, so the sum of the two acute angles for any right triangle are going to be 90. They're complementary. In figure 3, A and B are thus complementary, and we have established that sine of A is equal to cosine of B. This can also be written as follows. Yeah, so sine of A is equal to what? Well, we know that we could write B as 90 minus A because it's complementary to A. So there's a relation. Sine of A is equal to cosine of 90 minus A because B is 90 minus A. And so they call this a cofunction identity. And you could do the exact same idea with cotangent and tangent and secant and cosecant. But we're going to get 6 of these identities because so this is sine of A, but you could also look at like cosine of A is equal to sine of 90 minus A, right? You could just do it the opposite way. Sine of A is equal to cosine 90 minus A. Cosine of A is equal to sine of 90 minus A. And you could do the same idea with secant and cosecant and tangent and cotangent. And so that's the cofunction identities, trig identities. The cofunction identities state the following. Cofunction values of complementary angles are equal. So what does this statement mean? Well, they're calling these the cofunction pairs. Sine, cosine, tangent, cotangent, secant, cosecant. And so with that, when you think about cofunction values of complementary angles, they're going to be equal. So the sine of an angle is equal to the cosine of the complementary angle, which means the cosine of 90 minus the like sine of whatever is equal to cosine of 90 minus that whatever, and vice versa. The cofunction values of complementary angles are equal. The cotangent of an angle is equal to the tangent of the complement of that angle. So it would be 90 minus that angle. Or the tangent of an angle is equal to the cotangent of 90 minus that angle. Okay, write each function in terms of its cofunction. So yeah, cosine of 52 is equal to sine of 90 minus 52. Tangent of 71 is equal to cotangent of 90 minus 71. Secant of 24 is equal to cosecant of 90 minus 24. You just need to remember what the cofunction pair is. Like, what's the cofunction pair for cosine? What's the cofunction pair for tangent, secant, etc.? Solving equations using cofunction identities. Find one solution for each equation. Assume all angles involved are acute angles. So, yeah, what you're going to do is you're going to convert one of these to sine or cosine using the cofunction identity. Then you'll have like sine of something is equal to sine of something, and you set those equal. So we'll work a bunch of examples. How function values change as angles change. Figure 4 shows 3 right triangles. From left to right, the length of each hypotenuse is the same, but angle A increases in measure. As angle A increases in measure from 0 to 90 degrees, the length of the side opposite to A also increases. So the length of the hypotenuse is the same, but the length of Y increases. And so what does that mean? Well, if the hypotenuse isn't changing and the length of Y is increasing, but again, this isn't changing, well, then X has to be decreasing. The length of X has to be decreasing. If the hypotenuse length isn't changing. So if you think about the sine of angle A, then opposite over hypotenuse, but hypotenuse isn't changing, so sine of A is increasing. And we already have an intuition for this because we can think about the general definition, right? The general definition, what's happening as theta increases, we've talked about this, the Y is approaching, the Y starts at 0, but then as you increase towards 90, the Y is approaching the value of the radius. And then once you get to 90, Y equals the radius. Well, since sine is just strictly concerned with the Y value over the radius, then it's sine of A is increasing towards 1. It goes from 0, if this angle was really small, it's close to 0, and then it increases towards 1. Okay, as A increases from 0 to 90, the length of the side adjacent to A decreases. So yeah, it starts off, if you think about the cosine, it starts off where adjacent over hypotenuse, X is close to equal to the value of the radius. And it's positive too. It's not like you have minus X is equal to the value of the radius. It's all this is always positive. So with right triangles, the trig functions are always of the angles are always going to be positive, right? These are acute angles. And so if it's close to 0, then the cosine is close to 1 because the length of x is close to the length of r. As you increase, theta goes towards 90, x is getting small. But r is, you can think about not changing, but even if r did change, as theta increases, it's x is going to have to shrink in proportion to r. The larger theta is, then the smaller x is going to be in relation to r. So it just like sine went from 0 to 1, going from theta is equal to 0 to 90. Cosine is going from 1 to 0 as theta goes from 0 to 90. But when it comes to, if you want to think about this from the other angle, it's the exact same principle, but it's just harder to get a sense of it because the angle is oriented in a weird orientation. You have to think about, like, you could flip the triangle into the page around and put it in standard position and think about it that way, right? So like this angle, it would be, so as the angle increases, the opposite's getting bigger, right? So the sine of this angle is getting bigger. And this, as this angle increases, this angle is decreasing. So the cosine is getting smaller. It's the same idea. It's just, again, the orientation's different. And then tangent, so opposite over adjacent. As the angle increases, the opposite's getting bigger, the adjacent's getting smaller. So tangent's getting bigger. When theta is really small, the opposite is small, and the adjacent is like close to r, so it's getting close to 0. So the tangent of this angle goes from 0 to infinity. When theta is getting really big, it's the tangent of this angle is approaching and getting really big. Again, because the adjacent's getting really small and the y is increasing. Okay, and you could do a similar kind of analysis with cosecant and secant. I think we really developed the skills to do this kind of analysis in chapter 1. I think the only difference from what we did in chapter 1 was thinking about this from an angle that's kind of out of orientation from the standard position. But just practice yourself. It's the same idea. You just have to think about use the SOHCAHTOA definition. You kind of, as the angle is changing, what's happening to the opposite and the adjacent. And you could think about the r not changing, but you don't even have to think about the r not changing. If this angle is going to increase, the r is never going to be smaller than the x and the y, the hypotenuse, right? So with knowing that, you know that, and you know this relation, r squared is equal to x squared plus y squared. So knowing that, you could just think about what's going to be the proportion of like x divided by r, y divided by r as this angle changes. So what's happening to opposite over hypotenuse, adjacent over hypotenuse, etc. Okay, comparing function values of acute angles, determine whether each statement is true or false. Sine of 21 is greater than sine of 18. Yeah, it is. Sine starts at 0 degrees. If we're thinking about acute angles, at 0 degrees, sine is 0, and then it increases towards 1 as you approach 90. So here we do secant. We'll work a bunch of examples. All right, trigonometric function values of special angles. Certain special angles, such as 30, 45, and 60, occur so often in trigonometry and in more advanced mathematics that they deserve special study. We start with an equilateral triangle, a triangle with all sides of equal length. Each angle of such a triangle measures 60 degrees. Although the results we will obtain are independent of the length, for convenience, we choose the length of each side to be 2 units. Okay, so we're studying trig function values of these of 30, 45, and 60 because they occur so often. And we're starting with this equilateral triangle, which it's not a right triangle, but the angles of an equilateral triangle are 60 degrees. And the side lengths can be any. It doesn't matter what the side lengths are as long as they're all equal. But they're gonna choose them, the side lengths, to be 2 so we can do some calculations. Bisecting one angle of this equilateral triangle leads to 2 right triangles. Yep. This ends up, from geometry, this is if you did a bisector here that bisects this angle, that's going to be perpendicular. That's stuff we learn in geometry. At least that's the case for an equilateral triangle. And also, it's the case that, so this is a perpendicular and it bisects this leg. So this is 1 and this is 1. And these two angles are equal. Because it's like a, an equilateral triangle is, things work out well for equilateral triangles. Okay, so you end up getting these two right triangles with these are 30 degrees and these are 60 degrees for both triangles. And so then you can use the Pythagorean theorem to calculate the height, but again, the lengths, we could have started with any length. It wouldn't matter, but with the Pythagorean theorem, you get x is equal to root 3. And so now figure 6 here summarizes the results for a 30, 60, 90 triangle. So yeah, we're just using, we're trying to analyze we can use an equilateral triangle because the angles are always 60 for an equilateral triangle. We can use this triangle along with concepts from geometry to split this into two right triangles to analyze trig functions of the 30 degree and 60 degree angle. Because any right triangle with a 30 degree angle is going to have a 60 degree angle. And this is the result, and the lengths of the sides don't matter, but they chose 2 because this is the cleanest side lengths. 1 here and 2 here, right? That's 2 clean numbers, and then root 3. But we could have started with any side length. We could have started with all the side lengths equal to 5, and we would have gotten different numbers. It's the proportions are going to be the same. But the side opposite the 30 degree angle has length 1 in this case. The hypotenuse has length 2. The side opposite the 60 degree angle has length root 3. So they calculate trig functions for the 30 degree angle. But the idea is, though, for any 30, 60, 90 triangle, you're going to have, you can think about these are like the standard starting values for the side lengths, like when you think about it from the perspective of proportions. So like, in other words, the long leg is going to be whatever 2 divided by root 3 is, that's a number. So if you have a 30, 60, 90 triangle and you know the long leg is equal to 5, let's say, well, then you know the hypotenuse is going to be 5 times 2 over root 3. That's the idea. And then you know that the short leg is going to be half of the hypotenuse. So you would take if you have a 30, 60, 90 triangle and you know the hypotenuse length, it doesn't have to be 2, well, just divide that by 2, and that's going to be equal to the length of the short leg. That's the idea. Where they're saying these are special. We come across the 30 degree angle and the 60 degree angle often with right triangles. And so what they're suggesting is it's useful to, we can kind of remember these proportions. And, we could choose any proportions to be like the standard ones to memorize, but these are clean, right? 1, 2, they have a 1 and a 2 and a root 3. You could divide them all by root 3, let's say, but then you'd have 1 over root 3 and 2 over root 3 and 1 here. So this is cleanest. So anytime you have a 30, 60, 90 right triangle, you can think about these proportions of the side lengths. And with the side lengths, you can easily calculate what the trig functions are, right? Trig functions here's opposite, here's hypotenuse, here's adjacent. Trig functions here's opposite, here's hypotenuse, here's adjacent. Okay, so yeah, that was the 30 degree angle. Now they do the 60 degree angle, just SOHCAHTOA. Note the results in example 5 could also have been found using the fact that the cofunction values of the complementary angles are 60 and 30 degrees are equal. Yeah. Right? Every single pair of acute angles in any right triangle, you could think about the cofunction identities because those are complements. And they're complements and they're acute angles. So if we come back, so these cofunction identities were for any acute angle. I should have mentioned that. This is just for acute angles. Now, later in the course, we're going to analyze these for any angle, not just acute angles, but for the moment, we've only defined these for acute angles. We haven't analyzed if these are true for non-acute angles. Okay, so now what about the 45 degree angle? So they mentioned the 30-degree angle, the 60-degree angle, and the 45-degree angle occur often in trigonometry. We just analyzed the 30 and 60-degree angle. What about the 45-degree angle? So here's a 45, 45, 90 right triangle. So they start by creating a 45, 45, 90 right triangle. This triangle is isosceles. For simplicity, we choose the lengths of the equal sides to be one unit. Yeah, so it's isosceles, so that we know that the side lengths opposite of the angles are going to be the same. So for convenience, they make those one and determine, okay, so what's going to be the hypotenuse? That's root 2. So, the side lengths could be, you could choose the side lengths, these two equal side lengths to be anything. But they chose 1, and now the radius is root 2. So there's like the base side lengths for a 45, 45, 90 triangle, right? So like if you have any 45, 45, 90 triangle and you know the length of one of the legs is 10 or whatever, 15, well, then you know the other side length is going to be equal to 15, and then you know the hypotenuse is going to be equal to that side length times root 2. It would be, if the side length was, this side length was 10, that means this side length is 10. That means the hypotenuse must be 10 root 2. And again, the trig functions is easy. So use SOHCAHTOA, opposite over hypotenuse, adjacent over hypotenuse, etc. And obviously, it's the same angle, so either angle is going to have the same trig function values. Okay, so here they list out the trig function values of 30, 45, and 60 degrees. Okay, note you will be able to reproduce this table quickly if you learn the values of sine 30, sine 45, and sine 60. I mean, you don't have to memorize those, but they're saying that if you memorize those, then you can complete the rest of the table using the reciprocal identities, cofunction, and quotient identities. Okay, a calculator can find trigonometric function values at the touch of a key. So why do we spend so much time finding the values for special angles? We do this because a calculator gives only approximate values in most cases instead of exact values. A scientific calculator gives the following approximation for tangent 30. I don't think so. So, okay, we're in degree mode. So there's an exact value. So I'm not sure what they're referring to here, but yeah, I mean, you deal with those angles a lot in science and engineering, 30, 60, 90 triangles. So why not kind of break them down a little bit more than the other angles? All right, so now let's work some example problems.